Often in the laboratory, reactions are performed where gases are collected over water. Since we're beginning the gas unit with an experiment where we're collecting gas from a reaction, I'm going to introduce a new piece of equipment today along with two different formulas that we'll be using in the calculations of the lab. Unfortunately, we will not be collecting the gas over the water of Lake Michigan, but we'll be collecting over some water in the lab. First, the reaction that we're going to be doing. The reaction we're doing is one you're familiar with. What we're going to do is take some magnesium, which we have right here, solid magnesium, and add to aqueous hydrochloric acid. And the product of that reaction would be magnesium chloride and hydrogen gas. Now here's the unbalanced reaction. A couple things to notice. Remember, hydrochloric acid is aqueous. What that means is there are actually hydrogen ions, which we simply represent as H+. And there's also chloride ions, which we represent with just a Cl- that are floating around in water. Water is mostly composed of water molecules with these mixed in. And when that reacts, we're going to produce magnesium chloride. You do not see anything because magnesium chloride is just like if you dissolve salt in water. Magnesium chloride ions are floating around at a 2-to-1 ratio with 2 chloride ions for every 1 magnesium ions in the water that we see here. Now, I've sort of represented that right here. And on the top of that, we see bubbles, and the bubbles represent the hydrogen gas. Now, this is what we're interested in collecting, is this hydrogen gas, and that's what we're going to do in the lab. Now, in the past, we see if we drop magnesium in hydrochloric acid, which is happening right here, you all of a sudden see bubbles. And this happens with other metals as well. For example, if you drop zinc in hydrochloric acid, you'll produce hydrogen gas. But we did a reaction similar to this if you think back when we did the lab on stoichiometry. Now, this was more, we looked at the amount of hydrogen gas that was in this balloon. We actually did that more qualitatively, like we were trying to qualitatively determine what was limiting reactant by how much gas was collected in the balloon. Now, in this lab we're going to be performing on Wednesday, we'll actually look at the volume of the gas much more quantitatively. What we're going to do is use this is the third one, the third photograph out here, we're going to use a gas collection tube. And with the gas collection tube, we're actually going to be able to calculate or record the volume of the gas collected, which will be specifically hydrogen gas, with 2 places to the right of the decimal. So this is going to be a much more quantitative measurement that we're taking as opposed to just looking and seeing how much gas was produced. So the gas collection tube is also called a eudiometer. So it's a eudiometer, that's what we see there. It's aka gas collection tube. A couple things about it. It sort of looks like a hybrid between a graduated cylinder and a test tube. So it looks like a long test tube, but there's going to be markings on the side where we will measure volume. Now, a couple things about this. It's going to be used to accurately measure any volumes of gases in milliliters, and so like I said, we're going to be able to record our volume measurement with 2 places to the right of the decimal. So that means we're going to be able to record numbers like, let's say, 41 point, then there will be a decimal point, 0.1, and then will be milliliters. So notice we'll be doing this with 2 places to the right of the decimal. Now the other thing is we're going to use this in an inverted or upside down position, and we're going to hold it with a burette clamp. We're actually going to do this part of the experiment in the sink. So we have these big rubber stoppers we're going to put in the sink, and the eudiometer will be placed inside the sink where it will collect the gas. Now, there are 2 different formulas we're going to use, which we've never talked about because this is our introduction to gas laws. One is Dalton's law of partial pressure. Now, Dalton's law of partial pressure is really illustrated here. Like if we were to measure the pressure of the air, and this would actually, there's no units written here, and I do not like to write formulas without units, but this one, if we did it, would be in what we call kPAs. There's actually 4 different measurements for pressure that we're going to use for gases. kPa is one of those, which stands for kilopascals. So if we were to measure the pressure of the air, and what's recorded here is actually standard atmospheric pressure in kPa, 101.3. Air is actually composed of many different gases, and 5 of those major gases are listed here. The major component of air is nitrogen gas, which is N2, and the second major component, which is about 20% of air, is oxygen, which is O2. We see that listed here. There's our O2. And then smaller components, we have water. Now this would depend if you're at some place where it's humid, like when I lived in Atlanta, Georgia, or if you're in Arizona, that'd be a very small number. And then also there's carbon dioxide, which is given off by humans when they breathe. And then argon. Of course, carbon dioxide is also produced by combustion, so with more combustion from vehicles and exhaust plants, things like that, there's going to be more carbon dioxide produced. So if we were to write this formula for this, we'd say the pressure total is equal to the pressure of every single gas that is present at together. So it'd be the pressure of oxygen plus the pressure of nitrogen plus the pressure of argon gas plus the pressure of water vapor plus the pressure of carbon dioxide. Now, how does this fit into our lab? Well, in the lab, what we're going to actually do is collect water, the gas over water. And so when we do this, there's actually going to be, represent this little area at the top represents where the gas is collected. There's actually going to be two gases in there. Now, it says gas 1. That gas for us will, of course, be hydrogen gas, diatomic hydrogen gas. And the other thing we'll have is water vapor. So those are our two gases that we're going to collect. So the formula for us in the lab will be pressure total, which is PT, is equal to the pressure of the hydrogen gas we collect plus the pressure of the water vapor. Since we're collecting it over water, water will vaporize and go into the gas collection tube as well as the hydrogen gas. Now, a couple of things we have to think about. What is a pressure total equal to? That's really the atmosphere, the pressure of the atmosphere pushing down on the water here. So that's this pressure pushing down. Now, what you need to do is when you record this volume, there's an interface here between the air and the water. Now, also in the UDometer inside there's an interface between the water vapor, the gas collected and the water. So what you need to do is see where this line is much higher. You'll need to lower your test tube or the UDometer, the gas collection tube, to the point where the water level in the UDometer is equal to the water level outside, because the pressure of the gas from the atmosphere pushing outside or down on the water outside the UDometer is going to be equal to the pressure of those two gases right here pushing down on the inside. And so that's how we can say they're equal, because what we'll do is you'll look up on the internet the pressure of our area. So our area is Winnetka. You'll find the pressure, atmospheric pressure of Winnetka, and then that's going to be equal to the pressure of the hydrogen gas we collect plus the pressure of the water vapor, which we'll get from a table. So let's do a sample problem with Dalton's law of partial pressure. They're pretty straightforward. Here's a problem from our textbook. A tank of oxygen gas is saturated with water vapor at 27 degrees Celsius. The total pressure of the mixture is 722 millimeters of mercury. Now notice here we have a different measurement for pressure. One measurement is kilopascals. Here's yet another measurement, millimeters of mercury. And this is the measurement that we're going to use in the lab. The vapor pressure of water is 26.7 millimeters of mercury at 27 degrees Celsius. What is the partial pressure of the oxygen gas? So the formula for this would be pressure total is equal to the pressure of the oxygen gas plus the pressure of the water vapor. So simply what you're going to do is insert the values that are given. The 722 millimeters of mercury is the total pressure. The unknown values of pressure of oxygen and the pressure of water vapor is 26.7. And so when you subtract the 722 minus the 26.7, we get the pressure of O2 as being 695 millimeters of mercury. I'd like you to note three things here. This is how I'd like you to do the problems. First, you write the formula. So that's the first thing we did right here, write the formula. The second thing is you insert the value into the formula with units. So notice we put in the numbers and the unknown in every unit. Then the third thing you do is calculate an answer. So these are the three minimum things I'd like to see from everyone. Now in your answer, notice what we did is we have the answer with the correct number of sig figs, and we also include units. So 3 steps in your answer with the correct sig figs and the correct units. So let's do the other type of problem that we're going to be doing, or the gas law problem we'll be doing when we do the lab. The second type is something called the combined gas law. Now we're going to learn about multiple gas laws, so we're going to jump in right in this lab and do something called the combined gas law. The combined gas law is there's a value of P, V, and T. P stands for pressure, V stands for volume, and T stands for temperature. Now when you're doing this problem, you just have to make sure pressures are in the same units, your volumes need to be in the same units, but your temperature needs to always be expressed in Kelvin. And if you don't remember, we studied Kelvin, we used that temperature value earlier in the year. To convert to Kelvin, you just take the temperature in Celsius and add 273 to it. So here's how it's going to work in the lab. We're going to use experimental conditions, and these are things that you got from the lab. So let's start. First, we'll have the pressure of the hydrogen gas. Now, we just determined this because we took the atmospheric pressure and we subtracted the pressure of the water vapor. Next, we have the volume of the gas collected. Now, this is going to be directly from our data table, and hopefully you have two places to the right of the decimal when you record this value. And the last is the temperature. Now, for the temperature, what you're going to do is it's going to be the temperature of the water and acid mixture, and you're going to measure this temperature at some point during the lab. So these are all experimental conditions. Now, we want to convert these to what we call standard conditions. Now, remember the temperature, of course, is in kelvins. Now, standard conditions for this would include the pressure at standard conditions. Now, standard pressure, we're going to learn all these values later on, but standard pressure in millimeters of mercury is 760 millimeters of mercury. The volume is our unknown, and that's what we'll be solving for. So, actually, I realize I wrote ones on all these, but these all should be 2's in here. There should be a P2, a V2, and then finally, this should be T2 on there. I just noticed that. So these should be P2, V2, and T2. Now the T2 would be the temperature in degrees Celsius, but we need to convert that to Kelvin, and it's going to be, so standard temperature is 0 degrees Celsius. We'll just need to change that to Kelvin, so that'd simply be 273 Kelvin. So let's do a problem like this. In this problem, the sample problem, we take 24.3 millimeter sample of helium gas at 25 degrees Celsius and 1.01 atmospheres, and is heated to 500 degrees Celsius and compressed to a volume of 15.2 milliliters. What is the new pressure of the sample? So first we look at our initial conditions. Our initial conditions are our pressure. Our first pressure is 1.01 atmospheres. Our next is our initial volume, which is 24.3 milliliters. And next would be our temperature, and our first temperature is 25 degrees Celsius, which we need to change to Kelvin. We'll change that to 298. Now next we want to change it to our second set of conditions, so we'll just call these our new conditions. I believe when I typed this up, I put P1, V1, and T1, and we're going to change all these to 2 so we don't confuse ourselves. So our second pressure, and we're going to call this P2 here, is going to be what we're looking for, because this is actually the question asks what is the pressure of the sample, so that's our unknown. Our second volume is of 15.2 milliliters. And then finally, our new temperature condition is going to be 323 K, because we just take the 50 degrees Celsius and add that to 273. So what you could do is you could manipulate the problem and isolate the P2 from all the other variables and then insert, and that's what I did here. So what I did is cross multiplied, and I solved. I found P2 is equal to P1 times V1 times T2 divided by V2 over T1. So with all those values inserted, it would look like this. We have 1.01 atmospheres times the 24.3 milliliters times the temperature, the new temperature, which is 323 Kelvin. Notice this is our first pressure, this is our first volume, and this is our second temperature. And then we're going to divide those by V2, which is the new volume, which is 15.2 milliliters, and T2, which is, T1, which is 298 Kelvin. Insert all those values and solve, and you'll have an answer of 1.75 atmospheres. Now notice, once again, when we do the problems, 3 things we're going to try and do in every time in this unit when you solve problems. The 3 minimum things I'll look for will be 1, that you write the formula for the problem. 2, you insert the values with units, preferably with units, into the formula. And then the third thing is that you solve for the formula. Now when you solve it, once again, it needs to be in the correct number of sig figs, and we need to include units. And the units for pressure this time are going to be atmospheres in a specific problem. That's it. Look forward to lab on Wednesday. You guys have enjoy the rest of your weekend. Oh, one more time. And guest appearance by the pub. This is Bubba.